A 26 billion parameter AI model demands 52 gigabytes of high-speed video memory just to turn on. Welcome to The Freshers, your guide to modern systems. Standard consumer graphics cards carry only 8 gigabytes of memory, so launching this model causes an instant crash. Software fails because it insists on loading every weight matrix upfront. Picture a tiny spotlight stage with 52 oversized prop boxes crammed through a narrow backstage doorway at once. The doorway jams and the performance halts immediately. Yet, TurboFieldFlare runs this model on an everyday desktop card using under 6 gigabytes. It completely skips expensive enterprise cloud GPU rentals costing thousands per month. How can this engine stream a massive model without enterprise GPUs or long boot delays? Transferring a 52 gigabyte model file across system RAM creates a massive memory bandwidth bottleneck that chokes generation entirely. Text generation is autoregressive, meaning the neural network rereads all 26 billion parameters for every single token generated. The graphics processor sits 90% idle, waiting for weight data. System RAM transfers data at 40 gigabytes per second, whereas dedicated video memory reaches nearly 1,000. Physical motherboard bus speeds strictly throttle performance. PCIe solid-state drives read at 7 gigabytes per second, forcing a 2-second delay per token. Dragging heavyweight matrices back and forth across expansion slots causes complete execution stalls. If holding the entire model in memory chokes performance, what if we stop trying? The memory wall stops us from holding 52 gigabytes at once, but layer streaming opens the door by processing model layers sequentially. TurboFieldFlare flips inference architecture by recognizing that neural networks execute in strict step-by-step order. A transformer model consists of 32 structural building blocks called layers. Layer 5 only needs activation outputs from Layer 4. It never requires Layer 30 sitting in active memory during that calculation. Think back to our single spotlight stage. Only one actor stands under the spotlight while remaining props wait in dark wings. By maintaining a tiny fixed memory window on the graphics card, TurboFieldFlare streams and computes each layer sequentially. This modular design completely decouples total parameter scale from physical VRAM limits. Instead of waiting 45 seconds loading model files into system memory, TurboFieldFlare uses zero-copy memory mapping. Memory mapping, or MMAP, links disk file descriptors directly into virtual memory address space. The operating system creates virtual pointer maps without copying gigabytes of raw weight bytes into physical RAM upfront. Token generation starts in under 0.8 seconds. When execution reaches layer 1, the kernel fetches required weight pages directly from storage on demand. Once calculation completes, active layer eviction immediately deallocates GPU buffers. Stagehands clear the spotlight mark instantly so the next actor can step into the lit area. Memory consumption remains strictly flat throughout inference. Eviction keeps peak VRAM allocation locked at 5 gigabytes, completely bypassing the 52 gigabyte wall. Layer streaming proves we can run big models in small memory, but combining compression with prefetching makes it fast. Raw storage read speeds traditionally choke real-time generation. Weight quantization compresses 16-bit floating point parameters into 4-bit integers, reducing file footprint by 75%. A 52 gigabyte model file shrinks down to 13.5 gigabytes in GGUF format. At 7,000 megabytes per second, a modern NVMe SSD reads a 400 megabyte layer in 57 milliseconds. That layer transfer completes faster than a human blink. Asynchronous prefetching issues background read requests for layer 2, while GPU tensor cores execute layer 1 math. Stagehands assemble the next prop in dark wings beforehand, hiding disk transfer latency completely behind GPU execution. By combining zero-copy mapping with active layer eviction, our VRAM footprint stays locked at 5 gigabytes. Now we must keep independent hardware engines operating in parallel. Pipeline parallelism divides VRAM into two double-buffered slots, alternating computation and transfer tasks simultaneously. VRAM slot A computes math, while VRAM slot B receives streamed data. Direct memory access enables the GPU DMA engine to pull pin system memory without CPU involvement. Sustained transfer rates over the PCIe bus reach 28 GB per second. Operating system page caching retains layer data in host RAM, boosting bandwidth to 30 GB per second. Total processor utilization stays under 5% while maintaining full streaming speed. Express conveyor belts feed props continuously while the actor stays in the spotlight. Having mastered the streaming mechanisms, we now measure real-world performance against hardware limits. Layer streaming will not replace a $20,000 server cluster. Enterprise data centers run models across 8 80-gigabyte GPUs in high bandwidth memory at over 100 tokens per second. However, TurboFieldFlare completely transforms everyday consumer hardware. On an NVIDIA RTX 3060 graphics card, a 26B model generates 15 tokens per second consistently. That generation speed matches comfortable human reading pace. The fundamental engineering trade-off exchanges peak generation speed for total hardware accessibility and a 90% reduction in VRAM. Prompt prefill latency takes longer because initial tokens must pass through all streamed layer weights sequentially. Instead of renting enterprise GPU clusters, you operate an efficient local workbench. While storage bandwidth limits maximum speed, local streaming completely changes the economic equation for AI. Advanced AI reasoning stops being a paid cloud API subscription. Developers can run 26B parameter coding models locally on laptops without exposing proprietary source code to third-party services. Private financial and medical documents stay completely offline and secure. Recall our opening scenario where a 52-gigabyte model crashed consumer graphics cards with out-of-memory errors. Smart software orchestration bypasses that physical hardware barrier. Automated software agents run overnight batch processing jobs locally, eliminating expensive per-token cloud API billing entirely. High-intelligence AI reasoning transforms into personal software owned by individual developers. Local community theaters can now stage full Broadway productions using one well-managed spotlight stage. Running a 26 billion parameter model isn't about buying bigger hardware, but using existing hardware far more intelligently. TurboFieldFlare conquers the 52-gigabyte memory wall through 6 integrated techniques: layer streaming, zero-copy MMPAM, 4-bit quantization, async prefetching, OS page caching, and PCIe DMA scheduling work in perfect harmony. Our single spotlight stage operates smoothly and flawlessly. As AI models scale larger, the future belongs to engineers who build smarter inference software systems. Software orchestration unlocks frontier reasoning capabilities on everyday desktop computers right now. That is how TurboFieldFlare streams giant AI models on consumer graphics hardware. If you enjoyed this deep dive into AI inference optimization and modern system engineering, hit subscribe to The Freshers for more hands-on breakdowns of cutting-edge software architectures.